In this video we're going to describe a way to take two groups and make them into a new group called the Cartesian product. So the way we do this is via the definition you can see on screen there. We start off with two groups, so let's say G star and H triangle, and then we define the Cartesian product by giving the set on which a binary operation is going to be defined and then describing what the binary operation is. So the set is just the Cartesian product of the sets G and H. That is the collection of all ordered pairs where the first element comes from G and the second element comes from H. And then on that set, if we want to define a group, we've got to give a binary operation, and here it is. So I've written the binary operation just by putting these two elements of the Cartesian product side by side, and the way it's defined is that the value of the binary operation where the first input is GH and the second input is G prime H prime is the element of G cross H, where the first entry is G combined with G prime under the group operation in G, and the second entry is H combined with H prime under the group operation in H. So this is not any use to us unless it actually does form a group. So let's try and verify that this really is a group. So this is a group. So we have to verify the three group axioms, and the first group axiom is the axiom of identity. So I have to produce an identity element and check that it satisfies the identity axiom, and the obvious candidate for the identity element is the ordered pair where the first element is the identity from the group G and the second element is the identity from the group H. So let's let EG be the identity in G and EH be the identity in the element in the group H. Okay, so I claim that the ordered pair EG-EH is going to be the identity, so I have to check that it behaves like the identity. So I have to multiply it on either side of a typical element of G cross H. So let's let X, Y be an element of G cross H. So we're going to try EG, EH times X, Y, and of course using the definition of our binary operation on our set G cross H, that's EG star X, EH triangle Y, and of course EG is the identity element in X in G, so EG star X is just X again, and EH is the identity element in H, so EH triangle Y is just Y again. Okay, so this element EG, EH does satisfy the first half of the identity axiom. So let's do this the other way round. The other part of the axiom of the identity is that XY combined with EG, EH should be the same as XY again. But of course the same thing is going to happen. The definition of the product is that this is X star EG and Y triangle EH. But of course, since EG is the identity in the group G, X star EG is just X again, and since EH is the identity in the group H, we get Y again here. Okay, so the element EG, EH satisfies the identity axiom. It is the identity element in G cross H. Okay, so the identity axiom was fine. Let's check inverses. So for the inverse axiom, I have to show that every element of G cross H has an inverse. So let's pick an element, X, Y, in G cross H. And of course there's an obvious candidate for what the inverse should be. The inverse should just be X inverse Y inverse. So then if we just check that really works, X, Y times X inverse Y inverse is, by definition, that's x star x inverse y triangle y inverse, and x inverse was the inverse of x, so what you've got there is EG, and in the second position y inverse was the inverse of y, so y triangle y inverse is just EH, and that's the identity element in G cross H. And on the other hand, if you work it out the other way round, x inverse y inverse times xy will, for the same reason, be EG EH, which was the identity element in G cross H. So the inverses axioms hold. For every element xy in G cross H, we can find another element, specifically the ordered pair x inverse y inverse, such that if you combine those two elements either way round using the binary operation we defined on G cross H, you get the identity element EG cross EH, and that means the identity axiom is okay. So finally, associativity. So let's take 3 elements in G cross H. So let's say x1, y1, x2, y2, and x3, y3 be elements of G cross H. And I have to look at the 2 different ways of composing these using our binary operation on G cross H and check that they give the same result. So let's do that. x1, y1 composed with, and multiplied by, however you want to say it, x2, y2, x3, y3 in brackets is, so we do the thing in brackets first, x1, y1, and then this composed with x2 times star x3 and y2 triangle y3. So again, by the definition of our binary operation on the set G cross H, that's x1 composed with x2 x1 star x2 star x3 comma y1 triangle y2 triangle y3. And if we do this the other way round, so the other possible order of applying our binary operation is to do x1 y1 and then x2 y2 and then combine that with x3 y3. And of course, if you work this out, what you're going to get is x1 star x2 star x3 in the first position and y1 triangle y2 triangle y3 in the second position. But if you look at the 2 elements we've got, well, in the first positions you have x1 star x2 star x3 and x1 star x2 star x3. But those 2 things are equal because the binary operation star is associative because G star was a group. And similarly, in the second position, you've got y1 triangle, y2 triangle, y3, and y1 triangle, y2 triangle, y3. But those things are equal because triangle is associative because H was a group. So these are equal. As G star and H triangle are groups. Okay, we really do then have a group. We checked all 3 group axioms, so what we have is a new group called the Cartesian product of G and H. So let's work some examples of Cartesian products. Let's look at some examples which come from forming Cartesian products of cyclic groups. So we're going to get some practice using the definition of a cyclic group of a given order that we looked at in our lecture on cyclic groups. So let's start with C2 being a cyclic group generated by an element G, like this. Okay, so this, you'll remember, was as a set, this just consisted of the elements E and G, and because this was C2, a cyclic group of order 2, this element G had order 2, so G squared was the identity E again. So if we take C2 cross C2, that consists of all the ordered pairs where the first element and the second element come from C2. So this has got 4 elements, E, 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 G, G, E, and G, G. Those are all the possible ordered pairs where the first and second element come from our cyclic group C2. And of course, in general, the size of the Cartesian product of G and H will be the size of G multiplied by the size of H. So here is our group. Let's just have a think about how this group behaves. Let's look at the orders of elements in C2 cross C2. So what happens if I take a typical element of C2 cross C2? Well, a typical element looks like, in the first position you've got a power of G, and in the second position you've got another power of G. So let's say G to the I and G to the J, where we can assume actually that I and J are 0 or 1. Well, if you take this element and you square it, what have you got? G to the I, G to the J, combined with G to the I, G to the J. That's what the square of a group element means. Combine it with itself under the group operation. And so, using the definition of the group element, the group operation on the Cartesian product, you've got G to the I times G to the I in the first place, so G to the 2I. And in the second place, you've got G to the J times G to the J. So again, using the exponent laws, that's G to the 2J. But an even power of G is the identity. Remember, G is an element of a cyclic group of order 2. G squared is equal to the identity. So is G to the minus 2, or G to the 4, or G to the 8, whatever. So what we have here is the identity element in C2 cross C2. So what we've shown here is that every element has order at most 2, because every element squared to the identity. Okay, every element squares to the identity, so that means the order is at most 2. It's 1 or 2. So take a look at the lemma which I copied at the bottom of the screen there. A finite group is cyclic if and only if it contains an element whose order is the size of the group. Here we've got C2 cross C2 in a group of order 4, and we've got every element having order 1 or 2. So there certainly is not an element with order 4, and that means this group is not cyclic. On the other hand, C2 is abelian, and it's not too difficult to check that if you take the Cartesian product of 2 abelian groups, then the result is abelian. So here is another example of a abelian group which is not cyclic. I mean, in fact, it's the same example in disguise as the 2 examples you already saw. And if you want to know what I really mean by disguise, well, this disguise means that the groups are what is called isomorphic. Now, unfortunately, we don't have time to do isomorphisms and homomorphisms of groups in 0007, but if you want to learn more about it, then you can search for group isomorphism or group homomorphism. Anyway, let's take another look at a Cartesian product of 2 cyclic groups. Let's let C2 again be generated by an element G. And let's now have another cyclic group of order 3, which is going to be generated by an element X of order 3. So then, if we look at the Cartesian product C2 cross C3, this time it's going to have 6 elements. 2 times 3 is 6 elements, and those elements are all ordered pairs where the first element comes from C2 and the second comes from C3. So we could have identity, identity, identity X, identity X squared, or we could have G identity or G x squared, gx, or gx squared, and that's it. Those are our 6 elements. Okay, so this time, let's think about the orders of some elements this time. So let's look at the order of gx. So we'll try and work this out. So if we want to know the order, we just have to work out some successive powers. So let's do that. Gx squared. Well, this is gx times gx. So of course that's just the same as g squared x squared, and this will work always. If you take gx and you raise it to the power n, what you're going to get is g to the n, x to the n. So we're going to use that as a shortcut to compute these powers. But anyway, let's think about what we've got here. G squared, well, G was an element of a cyclic group of order 2, a generator in fact of C2. So G squared is the identity in C2. On the other hand, x squared, that's just x squared. So there's the square. So let's look at the third power, gx cubed. Like as we said, this is the same as g cubed x cubed. Now g had order 2. G squared was the identity, so g cubed is g again. And x cubed, well, x is in a generator or a cyclic group of order 3, so x cubed was the identity. So here we've got ge. Fourth power, gx to the 4 is g to the 4 x to the 4, which this time g to the 4 will be the identity, and x to the 4 will be x again, because x cubed is the identity. And if we do the fifth power, g5 x to the 5, well, g5 will be g and x5 will be x squared, because x cubed is the identity. And finally, gx to the 6 is g6 x to the 6. G has order 2, so g to the 6 is the identity. X has order 3, so x to the 6 is the identity. Finally, we got back to the identity element in C2 cross C3 for the first time, so we found the order. So gx has order 6, because 6 was the first power, which was equal to the identity, the first positive power of gx, which was equal to the identity element in our Cartesian product. Okay, so this group is cyclic. We found that C2 cross C3 contains an element whose order is the same as the size of the whole group, namely 6. C2 cross C3 then is cyclic. So that's interesting. C2 cross C2 wasn't cyclic, C2 cross C3 was cyclic. So this poses an interesting question, which you should think about under which conditions on A and B is CA cross CB cyclic. So something to think about. All right, let's move on. Let's think about some applications of the big theorem we did in our last lecture but one, namely Lagrange's theorem. So you'll remember Lagrange tells you that the order of a subgroup of a finite group divides the order of the group. And we're going to use that to study the following problem, which is to find all subgroups of C2 cross C3, which we're going to write this time as C2 generated by an element x of order 2 and C3 generated by an element y of order 3. So we know that the size of this group, whose subgroups we're interested in, is order 6, and we know Lagrange's theorem. So what did Lagrange tell us? Lagrange told us that all subgroups have an order dividing the order of the group. Lagrange tells us that if H is a subgroup of C2 cross C3, then the size of H must divide the size of C2 cross C3, which is 6. So, possibilities. It's got to be a divisor of 6. The divisors of 6 are 1, 2, 3, 6. Okay, so what we're going to do in order to systematically search for all subgroups of C2 cross C3, we're just going to work one order at a time, and we're going to pick off the easy orders first of all. So case 1, what happens when the size of H equals 1? Well, if you're a subgroup, you've got to contain the identity element. That's part of the definition of being a subgroup. So if you're a subgroup of order 1, you've got to be just the identity element. So then, in this case, H must be just the set containing the identity element. Okay, that's the only possibility then for a subgroup of order 1. So case 2, the other easy case, is what happens when the size of H is 6. Well, if you've got a subset of C2 cross C2 of size 6, it has to be all of C2 cross C3. Let me say that again. If you've got a subset of C2 cross C3 of size 6, well, it must be all of C2 cross C3 because C2 cross C3 itself has size 6. So then, the only possibility is that H must be all of C2 cross C3. Okay, any group is a subgroup of itself, and it's the only subgroup of itself whose order is the same as the order of the group. So now the problematic cases are what happens when the size of H is 2 or 3. So let's do what happens when the size of H is 2. Okay, we have some thought to do. So let's think what we have here. We have a subgroup of size 2. So H must consist of, well, every subgroup contains the identity. So it's got to have the identity element, which is EE. And it's also got to have another non-identity element. So let's call that other element A. Now, you know that in a group, the order of any element divides the order of the group we're thinking about. So an element A inside a group H of order 2 has got to have order dividing 2. And if A is not the identity element, it can't have order 1, so its order must be 2. So where A has order 2. So let's write that as O of A equals 2. And in fact, any such set consisting of the identity and an element of order 2 will be a subgroup because it's the cyclic subgroup generated by that element A. So every subgroup of order 2 looks like the identity together with an element of order 2, and every element of order 2 gives you a subgroup consisting of itself and the identity of order 2. So these are precisely what the subgroups of order 2 look like. All we have to do to find them is to look for the elements of order 2 inside H. So our question is, which elements in C2 cross C3 have got order 2? Alright, well, let's work it out. A typical element of C2 cross C3 looks like x to some power, y to some power, like this. So if it's going to have order 2, then its square must be equal to the identity. So let's just work out its square. Its square is, using the exponent laws, x to the 2i, y to the 2j. And x has got order 2, so x to any even power is the identity. But on the other hand, we've got to have y to the 2j. Okay, so if this is equal to E, well, y to the 2j is equal to the identity. So actually, let's say this a bit more precisely. So this equals the identity element in C2 cross C2 if and only if y to the 2j is equal to the identity. And y has got order 3, so the powers of y which are equal to the identity are powers which are multiples of 3. So if this is true if and only if 3 divides 2 times j. Okay, but an integer j is, well, if you have an integer j, then 2 times j is a multiple of 3 if and only if j is already a multiple of 3. That's true because 3 is a prime number. And if j is a multiple of 3, well, y to the j is the identity because y had order 3. So the only elements of C2 cross C3 with order at most 2 are x to the something, and then we saw that power j actually had to be y to the power a multiple of 3, which is the identity. So the only elements you get with order at most 2 are x to the I e. And of course, the only different elements you can get there are x to the 0 and x to the 1. So you can have x, e, and e. Alright, so that means actually there's only one subgroup of order 2, which is the one generated by xe. Okay, what did we do there then? We said that a subgroup of order 2 must consist of an element of order 2 together with the identity element EE. We found that the only element of C2 cross C2 with order 2 was xe, and we did that by looking at which elements could square to the identity, and we therefore said that the only subgroup of size 2 is the one that consists of EE and our only element of order 2, which was xe. So we're done with case 3. We're on to case 4, which is which subgroups have size 3. Well, let's think about what an element of order, what a subgroup of order 3 looks like. It has to have the identity in it, and it has to have another element in it which is not the identity, at least one other element which is, well, in fact, exactly two other elements which are not the identity. So let's think about the order of a non-identity element of H. So what is the order of a non-identity element of H? Right, the order of an element of a finite group divides the order of that group. So the order of a non-identity element, well, it's not 1, but it's a divisor of the size of H, which is 3. The only things which divide 3 are 1 and 3. So the order of a non-identity element of H must be 3. Okay, on the other hand, if you have a non-identity element in H and that thing has order 3, then its first 3 powers, the identity itself and itself squared, are all different, so they make up all of H. So that means H must actually be the cyclic subgroup generated by one of its non-identity elements. So what we need to do now is just look for which elements have order 3. We need to look for elements of C2 cross C3 which have order 3, and let's do that on a new page. So we had, remember, C2 cross C3 was equal to x cross pointy brackets x cross pointy brackets y, like this. So x was an element of order 2, y was an element of order 3, and the question was which elements have order 3. Okay, we'll write down a typical element. Typical element looks like x to the I, y to the j for some integers I and j, and we're going to cube this and see whether we get the identity or not. So if I cube this, I get x to the 3i, and if I cube y to the j, I get x to the 3j. Okay, again we can say a little bit about this. Y was an element of order 3, so y to the power 3j, that's y to the power a multiple of 3, that's the identity. On the other hand, well, let's think about x to the 3i a little bit first. If I is even, then what you get here is x to the power an even number, so that's the identity because x has order 2. But if x is odd, then if I is odd, then 3 times I is still odd, so this would not be the identity. So if x to the 3i is equal to the identity in C2, 3i is even, so I is even. So it must be that x to the I is actually already the identity. Okay, so in order for x to the I, y to the j, all cubed to be the identity element, well, we need I to be an even number, so x to the I to be the identity, and we've got no condition at all on j. So the elements with third power equal to our identity element EE are must be the identity in the first place, and then y to the anything in the second place. And of course this will have order 3 if and only if j is not a multiple of 3. So EY, EY squared. And that's it. Those are the only powers of y which are not the identity. Okay, so we decided our subgroup of size 3 had to be generated by an element of order 3. So the possible subgroups of order 3 well, they are the cyclic subgroup generated by E and Y, which is EY to its 0th power, EY to its first power, and EY squared, which is EY squared, and the cyclic subgroup generated by EY squared. Again, let's think what we get. This is an element of order 3, so the cyclic subgroup it generates is EY squared to the 0th power, EY squared to the first power, and EY squared squared, which is E squared, which is E, and then Y to the 4, which is Y. Okay, this is the same thing as what we had before. These are equal. So actually there's a unique subgroup of order 3, just like there was a unique subgroup of order 2. So there's a unique subgroup, the cyclic subgroup generated by EY of order